Welcome to this section of the class where what we're going to talk about is graphing the trigonometric functions, the sine, the cosine, the tangent, etc. We're going to go through them, we're going to learn how to graph them, and that's going to become important because we're going to use this time and time again as you get into more advanced calculus and other topics. So let's go ahead and talk about it and see if what we can learn here. The first thing I'm going to do is I'm going to draw on the board what we kind of used a little bit earlier. I'm going to draw a little mini unit circle here because we're going to kind of use this, we're going to reference this. So this is a unit circle. You know, we call this axis the x-axis and this one the y-axis. And this is 1, this is -1 over here, this is -1 here, and this is 1. And so we draw what we call a unit circle, which just means it's a circle with radius 1. And if you remember back, that's how we derived, and my circle doesn't look too centered here on the axis, but that's not going to matter too much here in a moment. You remember we used this quite extensively just not too long ago when we talked about how do you take like the sine of whatever 30 degrees or the sine of pi over 6. Pi over 6 is equal to 30 degrees. And you kind of use the unit circle to kind of figure out where the angle is, and then by using that table that we had written on the board over here, we can figure out what this stuff is equal to. Okay, but one thing I want to point out to you is the following. Let's say we're working with 30 degrees. This is sort of a review here. This is roughly 30 degrees or something close to it right there. What you're doing when you have, and I'll draw a dotted line here, you know, some angle that you're looking at where this would be the angle here. What you're doing, as we talked about earlier, is to find the sine of the angle on the unit circle. What you're doing is you're just measuring this length here because sine is basically the y measurement here. Sine is related to y. If you were looking at the cosine of this angle, you'd be measuring this quantity here, which is the kind of the x direction, the x measurement. And so I taught you earlier that sine is related to y and cosine is related to x, and I told you that's very important. Here we're going to learn a little bit more why it's important. If you can imagine with me here, we'll kind of fix my unit circle here and we'll go on and talk about something pretty important. If you can imagine with me here a line here, an angle that defines an angle. There's some sine and some cosine that's defined here by the y measurement here and then the x measurement over here. As you move this line around the unit circle, the sine and the cosine are going to change. And that makes sense because we've already figured out how to calculate the sine and the cosine. But my question to you is, what's it going to look like as we rotate this line around this circle over and over and over again? Well, obviously here on the axis, the sine of this angle, which is 0 degrees here, is 0 because there is no y component here. And as we rotate here, the sine is going to get bigger and bigger because what we have here is the y component getting larger and larger and larger and larger and larger. Eventually it gets to 1. Okay, so up here at 90 degrees, or equivalently pi over 2 radians, the sine of this angle here is 1, positive 1. And then as we continue rotating down, the sine of this angle goes down again, because again, as we get on this side, the sine, which is the y component, gets lower. Eventually it goes back down to 0 again. So as you change the angle, the sine goes up to 1, which is its maximum, and then down to 0. And then as you come down here, it gets down to -1, and then back up to 0. And the purpose of this section of the class is to try to write that down and plot it and try to learn from it. So what we want to do here, and we'll do it right over here, what we want to do is we want to plot the sine of x, where x is an angle. Or actually what we'll do is we'll write it in terms of theta, so we don't get it confused. On this axis, I'm going to write theta. Okay, this is just an angle. Okay, so what we're going to have on the x-axis are angles. We're going to have, you know, pi over 2, pi over 4, pi over 6. We're going to have angles going out. And as we go to the right, we're going to get to bigger and bigger angles. As we go to the right on this graph, it's going to correspond to us rotating this angle bigger and bigger and bigger as we go to the right. On this axis, usually what we call the y-axis, we're going to have the sine of theta. Okay? So you can see the independent variable is the angle, and the dependent variable is just the sine of that angle, and we've already figured out how to calculate these. What we're trying to do here is just plot it. I've already taught you by looking at the unit circle that the sine of an angle is never going to get greater than 1, and I think you can convince yourself that it's also never going to get, on the negative side, greater than -1, or less than -1, depending on how you look at it, because these are all negative numbers less than -1. Okay. Here again you have positive angles that correspond to going this way, and on this side you have negative angles, -pi/4, -pi/2, etc., and they go this way because negative angles just go this way. Okay. So here at theta equals 0 right here, what we're going to do is we're going to write some things down. This is 0 radians. We're going to say this is pi over 2 radians. This is pi radians. This is 3 pi over 2 radians. And this we're going to say is 2 pi radians over here. Now let's figure out why did I pick these particular angles to write down on the board here. At 0 radians, you're right here in the unit circle. Okay, there's no angle at all, it's just 0. Here, if you remember, this is pi over 2. Okay, which is roughly 90 degrees, exactly 90 degrees actually. Here is 2 pi over 2, which if you look at 2 pi over 2, that just is equal to pi. So here you have, if you think about it, 0 pi over 2, pi over 2, 2 pi over 2, which goes to pi, and 3 pi over 2 down here. Of course, over here, this is 4 pi over 2 over here, which just reduces to 2 pi. Okay, so that's why I picked these. This corresponds to pi over 2 here. This pi corresponds to the angle being here. This 3 pi over 2 corresponds to the angle here. And then this 2 pi corresponds to coming all the way back to where I started, which is right here. Okay, so I picked very specifically on purpose angles that go around the unit circle one time. Okay, and let's see what we can learn from this. At 0 radians, my line is here defining an angle of 0 degrees. We've already learned that the sine of 0 is what? It's 0. The reason it's 0 is, if you look here, there is no, as you draw your line here, you're looking for a y component here in the triangle, and you're lying along the x-axis exclusively, so there is no y component. So your sine is just going to be 0. So let's put a dot here. At 0 radians, you have the sine of 0 is 0, so I just put it right there. As I sweep my hand up here to pi over 2, I'm looking for the sine of pi over 2 radians. I'm trying to figure out what is that equal to. That gets up here. Now again, my line lies exclusively along the y-axis, and remember sine is we're looking for the measurement along the y-axis, the projection along the y-axis, and that is fully lying along the y-axis, so that's equal to 1. So the sine of pi over 2, as we learned before, is equal to 1. So I'm going to go to pi over 2, and I'm going to put a dot right here, because I know at pi over 2, the sine of pi over 2 is just equal to 1, so I'm going to put a dot there. As I get over here, this is pi, so I'm going to be looking for the sine of pi, and I think you can figure out that since it again lies on the x-axis, I'm looking for the sine of pi. There is no y component there, so that's again just going to equal 0. Sine of pi is 0. And this is a little bit of review. I'm just kind of reinforcing things. So the sine of theta, when theta is equal to pi, is simply 0, so it goes along that axis there. And then finally, as we get down here, we've already swept around like this. We get around down to here. Okay, I'm looking for the sine of 3 pi divided by 2. And notice that as we get down here, my line lies again along the y-axis, and so I'm looking for a y component. It's purely negative because it lies along the negative y-axis here. So the magnitude here, since this is just a unit circle, is equal to -1. Sine of 3 pi over 2 is equal to -1. And we've kind of covered this some before. So at 3 pi over 2, the sine of that number is -1. So I've got a line there. And then again, as I continue around, I eventually get back to the x-axis again at 2 pi. And I'm looking for the sine of this, the sine of 2 pi. It's the exact same thing as the sine of 0 because I basically ended up where I started. So the sine of 2 pi, this is 2 pi here, and that's going to equal, again, 0. So the sine of 2 pi, I'm going to put 0. Now, we've picked just these special angles here to kind of give us the point, but if you were to fill in the blanks here and pick angles in the middle, and then angles in the middle here, in between, what you will find is that the sine of theta looks like this. It's a graph that goes up to 1 here, and then it goes down through 0, and then over through here, and then back up. And of course, this goes through that point right there. So this is what we call a sine wave, or a sine plot. This is what the sine looks like. Okay? At 0 degrees, it starts at 0. As you increase the angle, you know, like let's take an intermediate angle here. The sine, what we're looking for is this y component here of this triangle. Well, it gets bigger and bigger and bigger as you go up, 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 up. Eventually hits a maximum of 1 right here at pi over 2, and then it goes down, 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 down because, for instance, over here, this y component is less than it was here, so it's going down, 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 down. Eventually it gets to 0 right here, and then as we go down below, we're getting into negative y, so I'll use a different color for that. For instance, maybe over here, negative y. Well, again, I have a y component that's negative, so I start to dip below the axis here. Eventually I get to a maximum in the negative side of -1, and then as I complete my circle, I go back up and so that it's 0. And as you see, since this is a circle, I can keep going round and round and round, and this wave is going to repeat. It's going to repeat over and over and over again as I get to bigger and bigger angles beyond 2 pi. It's just a circle, so it's just going to repeat over and over and over again. Now, one thing I will say, you know, just to kind of drive it home is you also have the negative angles, negative pi over 2, negative pi, negative 3 pi over 2, and negative 2 pi. Of course, you can go back farther negative if you want. And really what you have is the same deal here. Okay? At negative pi over 2, it's going to be -1. The sine is going to be -1. Okay? At negative pi, which is going this way over here, it's going to be 0. At negative 3 pi over 2, it's going to be up here. And then as you sweep around negative 2 pi, it's going to be back to 0. So I will draw this as kind of a dotted line here. So then you have the negative side. So you can see as you go in the negative angles and as in the positive angles, you'll have a sine wave that repeats like this. Okay? A few things I want to kind of write down on the board that are really important. We have what we call the amplitude of this sine plot here, the sine wave. Amplitude is a big fancy word that means what is the maximum height of the thing? The maximum height is 1. Okay? It doesn't go higher than 1, and it doesn't go higher in the negative numbers than -1. So we'd say the amplitude is 1. We'll do some examples in a minute, but if the plot went up to 2 before coming down, then the amplitude would be 2. And just as a side note, as you listen to radio or listen to the stereo, okay, and you turn the volume up, you've got waves coming out of your speaker there. And as you turn up the volume, what you're doing is you're increasing the amplitude, the height of this wave, basically, which you then hear as a louder volume. So that's what amplitude is practically. You also have what we call the period of this wave, okay? And the period of this guy is 2 pi. What the period means is how far do I have to go before the wave starts to repeat itself, okay? And in this case, you can see it goes up and then down and back up, and it makes one complete cycle at 2 pi, okay? And so if I keep going here, I'll just get another cycle. And so the period is defined by this distance where it starts to repeat itself. If I had something that, repeated itself a whole great many times here, then the period would be different. But those are just some basic definitions for you. Okay, I'm going to erase this for now, but I'm going to leave the sign plot on the board because I'm going to use it here in a moment to explain some things. Okay, so let's move along and let's try to find what is the plot of the cosine function and see how it differs from the sine function. So what I'm going to do is I'm going to put that plot right underneath this one so that we can compare the two. Okay, what I'm plotting here is cosine of theta. Again, on this axis is theta, which are just angles. And again, I'm going to try to line these up. So I've got pi over 2, I've got pi, I've got 3 pi over 2, and I've got 2 pi. And again, it's not going to get any bigger than 1, and it's not going to get any bigger than minus 1. Okay. The reason I know this is because we're talking about a unit circle here, and we're just not going to get any bigger than 1. Recall, what does cosine theta means? What does that mean? It means take the angle, put it on this, draw some line that defines some triangle like the one we have here, and instead of looking at the y component, which is what we were doing here, we're going to look at the x component, which is defined by, for instance, this right here. This would be the cosine of this angle here. The cosine relates to x, and that's why that's very important. So let's look at 0 degrees radian. Again, my line is defined right here on the axis, okay? And notice that it lies fully along the x-axis. There's no component splitting it up into x and y as there is like up in this example. It's fully along the x-axis. So right away we see a difference. At 0 radians, the cosine is equal to positive 1. Okay, because it's fully along the x-axis. Immediately we start to see a difference between the two graphs right away. As we rotate up to pi over 2, up here, again we're looking for an x component here. There is no x component because this lies fully along the y-axis. So cosine pi over 2 is 0. As we continue over here to pi, I'm looking for the cosine of pi. I'm looking for the x component. It lies fully along the x-axis, but I'm in the negative direction. So the cosine of pi is simply negative 1. Okay. Eventually, I get down to 3 pi over 2, which is down here. I'm looking again for an x component. This has no x component because it's on the y-axis. So cosine 3 pi over 2 is simply 0. And then eventually I get back around to where I started, which was 2 pi radians, which is the same as 0 radians. I'm back to where I started. Cosine of this is 1, so then I put a value right here. Okay? So here is my basic plot of a cosine function. All we need to do is fill in the blanks. Okay? What we do is we start here, and we come down and we go through 0 to the maximum of minus 1, up through 0 again, and then end up kind of over here. This should be a little bit more curvy, like this. Okay? So that is basically the cosine function in the same region of angles as what we had already defined as the sine function. And at first glance, it looks totally different. I mean, it kind of has the same shape, but it looks quite a bit different. But let me open your eyes here a little bit, and let's go ahead and draw some negative angles and just see what happens. At negative pi over 2, and then at negative pi, and then at negative 3 pi over 2, and then at negative 2 pi. Well, if we continue logically and continue doing the same thing, what you will find is cosine negative pi over 2 is 0. Cosine negative pi is negative 1. Cosine negative 3 pi over 2 up here is again 0. And then cosine negative 2 pi again is 1. So if we were to continue the graph, it would come like this. Okay? Now it starts to look a little bit more familiar. Okay, so what you see right away is that these two graphs are related to each other. The sine graph kind of starts at 0 and goes up and then down. The cosine graph starts at 1 and it kind of goes up and down. The amplitude, which I'm just going to abbreviate amp for amplitude, for the cosine is still 1, the same as it was before for the sine function, and that's because it goes, again, to a maximum of 1 and -1 and back up, so it's the same, okay? The period is, again, still 2 pi, because if you look, after one complete cycle, you get back to 2 pi, so this is the minimum time it takes to start over again. If I were to continue, I would start right where I began there. So the amplitude and the period are the same. What is different between these two graphs is just simply the fact of the starting point. If I were to take this graph right here, this cosine graph, and shift it to the right, if you can imagine just grabbing the actual line, squiggly line here, and grabbing it and shifting it to the right, where this point were actually right here, then what you would end up with is a sine function. So the sine and the cosine function are related to each other, and to kind of show you how they're related, I'll just write one little thing on the board. Sine of theta is equal to cosine of theta minus pi over 2. I'm just writing this on the board to show you how you write a shift down. This is called kind of a shift formula. Anytime you have a cosine or a sine in parentheses, you have some angle in here, but inside you have an angle minus a constant. What it's saying is, and it's a little bit backwards from what you would initially think, but if it's theta minus an angle, it means you shift it to the right. If it's theta plus an angle, it means you shift it to the left. So because I have theta minus pi over 2, it's like telling me that all I do is I take this cosine graph and I take it and I shift it to the right by pi over 2. Notice I'd have to shift by pi over 2, and then what I would end up with would be a sine function. So that's why sine is equal to this quantity. This is called a shift formula. It's kind of not really all that necessary. I just thought I'd show you where that comes from. Okay, so now we have the sine and the cosine function, okay, which was, I think, pretty interesting, pretty important. Okay, let's go ahead and erase these things, and then we will go ahead and start monkeying around with these plots a little bit more to try to learn a little bit about them. Let's change the amplitude. Remember, the amplitude is how high the graph actually goes, how high and how low. Well, let's go ahead and change that. And so let me give you another graph. Instead of y equals sine of theta, let's say y is equal to 2 times the sine of theta. Okay, and the problem on the test says plot this. Immediately what you notice is that you have a sine theta, and presumably you'll know how to plot sine theta because we've just learned how to do that. The only difference is there's a 2 out here. So every place on that graph that we had a minute ago, every little point is going to be multiplied by 2. Okay? So first thing you should do is draw this, just kind of like how we had. You'll have pi over 2, you'll have pi, you'll have 3 pi over 2, and you'll have 2 pi. Okay? And we can also draw a little unit circle down here to help us figure out the other things here. Remember, this is a unit circle. So at 0 degrees, sine of 0, because I'm all on the x-axis here, is 0. And 2 times 0 is 0. So again, I start at the same point. We're plotting 2 times the sine of theta against theta here. Okay? As I move up to pi over 2, this is a unit circle again. Sine of pi over 2 is 1 because I'm fully along the y-axis. But I'm looking at 2 times the sine of theta, so 2 times 1 gives me 2. So if this is 1 and this is 2, this point would be up here. As I get over to sine of pi, again at 0, 0 times 2 again gives me 0, so my point's here. As I get to as I get to 3 pi over 2, sine of 3 pi over 2 is negative 1 because I'm along this axis down here, just like we found it before. 2 times negative 1 gives me a negative 2. So this point, 3 pi over 2 is at negative 2. And again, when I get back to 0, sine of 0 is 0. And 2 times 0 gives me 0. So all I did is I went around the circle, I figured out what the sine of the angle was, and I multiplied by 2, and I got this. If you were to plot this, you'll get something like this. It'll go up down through there, and it'll go up through here. If you recall, this graph looks exactly like the regular old sine function, exactly the same, except for the fact that it goes not up to 1, it goes up to 2. And that's what I want to show you here. Anytime you have a sine function and it's multiplied by some number, the only difference is you're going to have a regular sine function, but the highest it goes is going to be the number in front. And the lowest it goes is going to be negative of that number. Because remember, sine by itself just goes up to plus and minus 1. So anything you multiply by is going to make it go up to, if I had a 54 in front of here, it would go up to 54 and it would go down to negative 54. The period here is still 2 pi. That didn't change at all. Okay? So let's erase this, and we'll move on, and we'll try to monkey around with the period of the function, and I'll show you kind of how that works out here in just a moment. First thing to notice, though, is let's figure out what we're going to plot. So let's say the test has y is equal to the sine of 2x. Okay? Now, we don't have anything in front multiplying here, but I have something inside multiplying there. And you'll see that does change things a little bit. The easiest way to do that is to go ahead and draw my coordinate axis. In fact, let's make it even bigger. Let's move it over here a little bit. This is theta. This is sine of 2 times theta. Okay? The easiest way to do this is to make a little chart here. Theta and sine of 2 theta. That's the easiest way to do this right here. Okay? And then we can go ahead and plot a period. So let's take the ones that we know of so far. Let's go ahead and start there and see where we get. Pi over 2, pi, 3 pi over 2, and 2 pi. And let's see where we get when we do that. If theta is equal to 0, we're over here. Okay? What we'll have here is we'll still have sine of 0, because 2 times 0 is 0, and that's just going to equal 0. Remember, just like before. So I'm going to have a dot there. Okay? Let's say if I've got pi over 2, I'll have sine of 2 times pi over 2 is just going to give me pi. 2 times pi over 2 gives me pi. And if you look on our unit circle, if I'm over here at pi, remember this is pi, this is 3 pi over 2, and this is up here, pi over 2. Okay? Up here at the top. So, when I'm looking over here, I multiply the 2 in here, and then what I'm actually evaluating is sine of pi over here, which is 0. So that's 0. Okay? So this is 0. Okay? So then I'll look here at theta is equal to pi, then I'll have sine of 2 times pi, okay, which 2 times pi, if you remember, is back over here on the x-axis, which is again 0. You can see that there's going to be some problems here. I keep getting dots on the basically at 0, okay? If you plug in 3 pi over 2, you'll get another dot at 0, and if you plug in 2 pi, you'll get another dot at 0, because no matter what I put in here, like 3 pi over 2, 2 times 3 pi over 2 is 3 pi. 3 pi is going to be back here on the axis somewhere, and it's going to be 0. If I put in 2 pi times 2 is 4 pi. 4 pi would be, all the way back around here again, and it would be 0 again. So I've got a bunch of dots here. The way to overcome this problem is to pick some angles in between. What's between 0 and pi over 2? Well, it's pi over 4. So I'll pick that one. Let's see what we get here. Sine of pi over 4 times 2 is pi over 2. Sine of pi over 2. 2 times this, you can cancel the numerator and the denominator here, and you'll get pi over 2. Now, finally, I get something nice here. Sine of pi over 2 is 1, because this is pi over 2. Sine of that is 1. Okay? So if I put a pi over 4, then up here at 1, I'll finally have a 1. Okay? Notice that when I plot it, what I need to plot on the theta axis is this number here, but what I'm actually evaluating is something slightly different because I've got a multiplier in here. To get between this guy and this guy, it'll be 3 pi over 4 will be a number to put in there. Okay, let me get rid of this, make some room. Okay, we can draw another little unit circle kind of down here. Okay. Sine of 3 pi over 4, I need to multiply it by 2. 2 times 3 pi over 4, I'll just write it here. 2 times 3 pi over 4, okay, is going to be, this can cancel with this, with a 2. So this will be sine of 3 pi divided by, by 2. Okay, you see all I did was I multiplied this times 3 pi over 4, and kind of got something here. 3 pi over 4, I'll just draw a dotted line, is right here. Okay? Okay, so what I need to evaluate is sine of 3 pi over 2. Here I've got pi over 2, 2 pi over 2, 3 pi over 2. So that's just negative 1. So at 3 pi over 4, at 3 pi over 4, I've got a value of negative 1. Okay? Now you can start to see a pattern. Okay? Now you can start to see a pattern. This graph is going to start here. It's going to go up through this point, down through this point, down through this point, back up to 0. Okay? And if you were to pick more angles here, you'll find out it'll do it again over here. You'll find that up here there's a point, and down here there's another point. So we could kind of draw a dotted line up through here, and then down through here, and then up through there. Okay? Now look at this graph. It looks like a sine wave, and it is a sine wave. It just looks a little bit different than it did before. In the previous case, when we had sine of theta, it was one complete cycle that fit in this 2 pi region of angles here, and now you can see 2 complete cycles fit in here. So whereas before we had 1 cycle fit in the 2 pi region, here we have 2 cycles. The 2 cycles come directly from this number here. Okay? Basically, when you see a number in front of a theta like that, what it's going to mean to you is, whatever the number is, you're going to see that many number of waves in a 2 pi region. Okay? So here, if you look, the amplitude is still equal to 1 because it doesn't go bigger or smaller than 1, 1 or negative 1. And the period now is not 2 pi. The period now is simply pi. Okay, the reason the period's pi is because pi radians is the amount of an angle it takes to start to repeat your sine wave over and over and over again. Whereas before, on the original sine graph, the period was 2 pi. So you see, as you start putting numbers in here, you start modifying, you start squishing the graph together. If you had like sine of 100 theta, you would have 100 complete cycles of this wave in a 2 pi region here, and so on. So the bottom line is, the main thing that I really want to just point out here is that if you have like sine of something, if you put a number out here, what you're doing is you're changing the maximum amplitude that you go to. If you put a number in here, you're changing how many waves you get in here. You're changing the period. So whatever modifier you put out here, you change the amplitude. Whatever modifier you put in here, you change the period. And that's really the main lesson from that I really wanted to get at. Now notice that you can do the same analysis with the cosine function. It's all going to apply. You'll just go through a table and you can plot the graph. But the main thing for the cosine function is the same thing. If you were to take a cosine function and you put a number up in front, it would look exactly the same as the original cosine function, except it would go from 4 to minus 4 and back up to 4 again. And of course, if you were to put something on the inside here, you would change the period. You would make 6 complete cosine functions in a 2 pi period there. You would be changing the period. And of course you can have problems that change both at the same time, like what I have here. In this case, if I were plotting this, I would have a cosine function that would go from 4 to -4 and then back, and also on top of that, I would get 6 complete cycles in a 2 pi period. And so that's how you go about plotting these things. You look at your knowledge of the cosine and the sine function initially, and you use these modifiers to go ahead and plot it. And of course, you can get a graphing calculator out or something like that and convince yourself of that there too. And you can, of course, do a plot in a graphing calculator in a matter of seconds. But I think it's useful to know where the stuff comes from, and you'll be asked to do that kind of thing on a test. I have no doubt of that. Okay. Last thing we're going to do in this section is we're going to look at the other graphs out there. Secant, cosecant, cotangent, and all that. We're going to briefly touch on them. Once you know how to do the sine and the cosine graphs, which we've just learned, the other ones are really a piece of cake. So what if the test says something like plot the secant function? Okay? Remember from your rainbow, you have sine, cosine, tangent, cotangent, secant, cosecant. Okay, this is how I taught you to remember how these are related to each other. Okay? Secant, which is here, is just equal to 1 over, what? 1 over cosine. 1 over cosine. Okay? So let me show you how to plot that. I'll show you what I think is really the easiest way to plot these things. First thing you do is you plot what you know as a reference only, the cosine function. Well, we already did that. Here's pi over 2. Here's pi. Here's 3 pi over 2. And here's 2 pi. And of course, here's 1, and here's -1. And I'm going to help you out, speed things along a little bit here, but I think you can convince yourself that the plot looked something like this, and you'll get to the point where you can memorize these after a while. Cosine function starts at 1, goes down like this, goes up like this, like that. Okay? Now this is a reference. This is not the problem you're given. This is something that you're going to use to be able to help you graph this function. Okay? Now, notice that the secant is 1 divided by cosine. Okay? So I'm going to draw the actual secant function in blue to kind of change the color here so you can kind of see it. At 0 degrees, 1 divided by cosine, where cosine theta is given here by this line here. 1 divided by cosine, what am I going to put here? Well, cosine of 0 is 1. So 1 over 1 is 1. So for the secant function, I've got a dot at the same place. At pi over 2, 1 over cosine, basically I'm looking at every point on this line and I'm taking 1 over that point, and that's equal to the secant function. So here, cosine is 0. 1 over 0 is what? 1 over 0. You may have been taught a long time ago that this was undefined. This is actually infinity. It just means that it's a huge number. And you're just going to have to kind of learn that. Anytime you have 0 in the denominator, you might have been taught in algebra or other courses that, oh, that's undefined. Okay, that's not undefined. It's just infinity. It's an infinitely large number, and you need to know that. Okay, so at pi over 2, 1 divided by 0 is infinity. So I'm just going to basically put a dotted line here, and you'll see why I'm doing that in a second. I'm going to put a line, a dot way up here at the top. Okay, and in fact, what I'm going to also do is I'm going to give us a little bit more room. Y is equal to secant theta, which is equal to 1 over cosine of theta. Okay, so I'm going to put a dot way up here near what I consider to be infinity. Okay. All right. At pi, cosine pi is -1. 1 divided by -1, again, gives me -1. So I've got a dot right there. 3 pi over 2 is, again, at infinity. Okay. Okay, so there's going to be an infinity. kind of down here, and down here, okay? And then you'll see that over here, if cosine at this point is 1, 1 over 1 is again 1, and again you have this infinity here, okay? Now let me go and fill in the blanks and we'll just talk about it. The secant function looks like this. It goes up to infinity. Down here it starts at negative infinity and it goes up, it touches 1, and it goes back down to negative infinity. And then here it starts at infinity and then it goes down and touches 1. So the blue lines are the secant function, okay? If you were to take these dots here along this cosine, take 1 over them, you arrive at this, okay? You can see some points like pi over 2, cosine of pi over 2 is 0. Cosine pi over 2 is 0. So 1 over 0 is going to give you infinity, but it depends if it's plus or minus infinity, and that depends on where you're coming from. Up here, you know, I'm getting smaller and smaller and smaller. You know, I'm approaching 0 from the positive side, so I'm going to approach positive infinity. Okay? Over as I flip on the other side of that line, I'm approaching infinity from the negative side, and so my infinity is going to come from negative infinity up to positive 1 and down back to negative infinity again. Okay? And then over here, again, I'm approaching infinity from the positive side, so I've got a positive infinity, and I'm coming in like this. Basically, the way to do this is find the points that are the known points that kind of touch the cosine line. You put dotted lines everywhere you know where there's going to be a problem, which are going to occur at like pi over 2 because cosine pi over 2 is 0, and at 3 pi over 2 because cosine of that is 0. And then you just kind of draw lines up to infinity like this. That's what the plot's going to look like, and as you put it in your calculator or your computer, you will see that. These vertical lines here, these dotted lines, are called asymptotes. The graph approaches these lines very, very closely, but they don't actually quite get there because they go off to infinity, and then they kind of come up from the bottom like that as you jump on the other side of pi over 2. Okay? And the reason that it jumps from positive infinity to negative infinity is because, you know, if you look at your unit circle, I'm going to draw a little unit circle down here. This is pi over 2 up here at the top, right? Over here, as I'm approaching pi over 2, the cosine is positive because if I'm looking over here, the cosine is a positive number because I'm along the positive side of the x-axis. Okay, when I get here, exactly here, cosine is 0, and that gives me my infinity here, okay? But as I get on to the other side of this right here, like over here for instance, the cosine's negative because I'm looking over here in the negative axis here. As I get here, I'm looking at the cosine, I'm looking at the negative axis. As you sweep remember this is theta, so as you sweep your angle theta through pi over 2, you have a change in sign of your cosine from positive to negative. And exactly in the middle, you get infinity. So that's why when you take 1 over this number, you have a positive infinity here, and then here you have a negative infinity. It has to do with the sign change right there in the middle. For the secant, the cosecant, the cotangent functions and all that, you're going to see that time and again, really. I think after the first time here, I think you'll understand a little bit more about where it's coming from, but we're going to see that again here in just a minute. The next graph we're going to talk about is going to be the cosecant function. So what if we have y is equal to cosecant theta, and if you look over here, cosecant is 1 over sine, so that's going to be 1 over sine of theta. How do we plot that? Let's say this problem's on your exam. Well, the first thing you do is you look at what you do know, which is the sine function, and you draw that, and then you go from there. Okay, let's say this is 1, and this is minus 1. Let's go ahead and draw the sine function again. So what we'll have is we'll have pi over 2, we'll have pi, we'll have 3 pi over 2, and we'll have 2 pi. And we want to draw the sine function first. And I'll just help you out and kind of speed things along here. You got a point here, sine of pi is 0, sine of 3 pi over 2 is negative 1, sine 2 pi is 0. And you'll get to the point where you can memorize those as well. So you have the graph that kind of goes through there, down through there, back up there, 1 period, amplitude equal to 1. Question is, how do you get from this to the cosecant function, which is what we already talked about, is 1 divided by that. Okay? Well, if you look here, right here at the origin at theta is equal to 0, I have a problem because theta is equal to 0. And the sine of this number is 0. And I'm looking for the cosecant 1 over this, so 1 over 0, remember, which we said was infinity. Okay? So I'm going to have some point really high up here. Okay, that's going to be that point. Up high, what I mean by that is I mean up at infinity, because 1 over 0 is infinity. Okay? Here, at 1, at sine of pi over 2, which is equal to 1, 1 over 1 is equal to 1, so I've got that covered. And over here at pi, I know I'm going to have what we called an asymptote before as well, because that goes at 0 right there, so 1 over 0 again is going to be infinity. Okay? So what I'm going to have in this region is I'm going to be coming from infinity, coming down to 1, and then back up to infinity again. Because at this point, I have a discontinuity, 1 over 0 being infinity, 1 over 0 here being infinity, so I got to come from infinity, and I'm just going to come and touch the graph there. Okay? And you'll find that the same thing happens over here, okay? Because here, 1 over 1 is going to give me 1. And here I've got an infinity and an infinity, and so the only place I can really come from is negative infinity, which will come here. And again, I can kind of show you why you get this discontinuity. Why does it go all the way up to positive infinity and then jump from negative infinity? That has to do, again, with the unit circle. If you look at your unit circle, okay, and you look at the sine function, let's look at pi, because that's where the discontinuity happens. Pi is over here, okay? As you sweep your angle through pi, you'll notice like on this side of it, sine is positive because it's positive here. This is the y-axis. This is positive measurement. As you go through the angle pi, you get over here, and you have a negative sign. So as you move your angle through pi, the angle pi, you get a discontinuity in signs. It goes from positive to negative. Because it goes from positive to negative here, and because right at this point it's 0, you get this discontinuity at infinity and then again at negative infinity. Okay, so that's kind of what causes that. Only a couple more I really wanted to go through, which are tangent and cotangent. They have some infinities wrapped up in there too. I want to show you where those come from. And I think it'll help you on your test. Okay. What if we wanted to plot as a problem or something, y is equal to tangent of theta? Well, the first thing to realize is this is just equal to sine theta over cosine theta. And we've already kind of talked about that. Okay? Well, what you can do is first go ahead and draw your plot. This is theta, and we're plotting tangent of theta. Okay? Let's go ahead and write some angles now. Pi over 2, pi, 3 pi over 2, and 2 pi. Okay, the question is how do we proceed? It's sine divided by cosine. What you need to do in this case to plot this is look at how do sine and cosine behave. Okay, how do they behave independently of one another? Okay, well, look at 0. Let's go ahead and make a little chart for ourselves. Here's theta, and here's tangent theta. At theta is equal to 0, I'm going to put 0 into here. I'm going to get sine of 0, and I'm going to divide it by the cosine of 0. What's the sine of 0? Sine of 0, if you look back at your unit circle, is 0. And 0 over anything is just going to be 0. So I'm going to have a 0 right here. Okay? Tangent of 0 is 0. Okay? Now as I increase the angle here, eventually, when I get to pi over 2, sine, I'm going to draw a little unit circle here to help us remember. Sine of pi over 2, which is up here, is perfectly defined. That's 1. But cosine of pi over 2, which I need to divide by, is 0. So I'm going to have what we called one of those asymptotes here at pi over 2. Okay? I'm going to have one of those asymptotes. As the angle gets closer and closer to pi over 2, the denominator here goes to 0 because cosine pi over 2 is 0. So what you're going to have is, on this region, something that goes from 0 and it's going to go up to infinity. Okay? If you look over here at 2 pi, as I get or excuse me, as you get over here to 3 pi over 2, here's pi over 2, we had an asymptote there. As I get over to 3 pi over 2, I'm going to have the same problem. Cosine 3 pi over 2 is 0. And 0 in the denominator is going to give me a problem as far as asymptotes go, so I'm going to have another asymptote here, okay? And we just need to figure out what we have in the middle at pi. Sine of pi, which is over here, is 0, right? Cosine of pi is negative 1. But 0 wins out because 0 over anything is 0, so I've got a 0 here, okay? And then if you were to pull in additional angles, you would find that in the middle region it kind of goes through here and like this, okay? Now over here at 2 pi, again you'll find that tangent of 2 pi is 0 because sine of 2 pi, as we get all the way around to 2 pi here, sine of this is 0, which drives the whole thing to 0, and then you'll see that this goes up like this. Whoops, it goes up to this point here, okay? So that's the tangent graph.